Hello all, welcome back to Sri Sai Tech Edu YouTube channel, Read Lead Success. I am dealing with the subject Network Analysis and Control Systems. I have already uploaded Module 1, Module 2 and Module 3 of this subject in my channel. If you want to just check it out, you can visit my channel and check them. All Module 1, 2, 3 are available. Now I am continuing with Module 4, in which there are two chapters, that is time response analysis and stability analysis. First, we will see about time response analysis. Under time response analysis, you are going to study main three topics. In that, initial is introduction, and other three main topics are the time response of first order system, the time response of second order systems, and the response specifications of second order systems. We'll go by one. First, we will see what is time response. Introduction. The time response of a system is the output of the closed loop system as a function of time. It is the output of the closed loop system as a function of time. Time response means what? It is nothing but at which time the system is responding. When it will respond, when you will get to know how to find the response time, by the output of the system. From that you can get the time response, like how much time it took for the response, right? So the time response of the system is the output of the closed loop system as a function of time. The time response of a control system is usually divided into two parts. It has two parts. First one is transient response, second one is steady state response. Transient means it continuously changes. Steady state means it is at the steady state. It is not going to change. Let C of t denote the time response of a continuous data system. Let C of t be the continuous data system time response. Then in general form you can write Ct of t plus Css of t. Ct of t denotes what? Transient response. Css of t denotes what? Steady state response. Okay. Into control systems, transient response is defined as that part of the time response that goes zero as time becomes very large. The Ct of t has a property that limit t tends to infinity, Ct of t is equal to 0. The transient response becomes 0 as the time becomes very large. If this time is becoming infinity is nothing but large. Like when let limit t tends to infinity, when this is becoming large, when t becomes large, then the transient response will tend to become 0. Understanding? Then the transient response is also called the dynamic response of the system. Why? Because it is continuously changing. So it is dynamic response of the system. The steady state response is simply that part of the total response that remains after the transience has died out. Okay, the steady state response is simply that part of the total response that remains after the transience has died out. When this transient response is died out, when it becomes 0, then the total time response is nothing but steady state response. Understanding? Then we'll go to time response of the first order systems. Consider the first order unity feedback system shown in figure 4.2. If you see here, this is the first order unity feedback system. Physically, the system may represent an RC circuit. This is an RC circuit, thermal system or the like. A simplified block diagram is shown in figure 4.2b. The input-output relationship transfer function is given by. You know that in module 3 we've already studied what is the transfer function, output by input, nothing but C of s by R of s. If this is a block diagram, you know that if you consider this as G and this H is equals to 1, you can write by G by 1 plus GH. Why? Because as here it is minus, you will take it here as plus 1 plus GH. If you substitute that, what you will get? 1 by TS by 1 plus 1 by Ts, as H is 1, it is taken as 1. If you calculate this, what you get? 1 by Ts by Ts plus 1 by Ts. This TS get cancelled. The answer what you get 1 by TS plus 1. This is what the transfer function of the example that is taken here. In the following, we shall analyze the system response to such inputs as the input step, unit ramp, and unit impulse functions. The initial conditions are assumed to 0. All systems have the same transfer function, will exhibit the same output in response to the same input. As all, if you take as all as the same transfer function, it will exhibit what? Same output with the same input. Okay, with response to the same input. Now we will calculate for unit step, unit ramp, and unit impulse based on the transfer function. We will see how. See here. First we will consider what? Unit step response of first order system. You know that unit step has what? R of S as 1 by S. Am I right? So that the output response is given by, you know, C of S by R of S is given in the first equation. But if as R of S, if you substitute 1 by S, the 1 by S will go to here and becomes multiplication 1 by S into 1 by TS plus 1. Expanding the equation 1 into partial fractions. How we can expand into partial fractions according to maths? 1 by S minus 1 by TS plus 1 you can write. If you write in this way, again if you take LCM, you will get this only. Understanding? And what they have done here is 1 by, they have took the t common and cancelled this t, S plus 1 by t, 1 by t, it has become from this to here. Okay, taking the inverse Laplace transform. This is why we are doing this, because to take we need to take inverse Laplace transform. In order to take inverse Laplace transform, we can't do inverse Laplace transform directly for this. So that if you do like this, 1 by S plus A, it is in the form of 1 by S plus A. So inverse transform of 1 by S is what? 1. And inverse transform of 1 by S plus A. A is what? 1 by T. So it is e power minus AT. As A is 1 by T into T. Okay, 1 minus e power minus T by capital T. For T greater than or equals to 0. We need to consider. This states that the output rises exponentially from 0 value to final value of unity. From 0 value to final value of unity, it exponentially rises. It is rising. Why? Because if you see, this is exponentially rising. One important characteristic of such an exponential response curve C of t, shown in figure 4.3, is that if you see here, it is taken for t, 2t, 3t, 4t and 5t. If you consider, as you know, the C of t is equals to what we got, 1 minus e power minus t by capital T. Okay. Now what they are telling is, if you substitute t is equals to t, then what it becomes? 1 minus e power minus 1. So you get value of what? 0.632. If you calculate in Calci, if you get, you will get a 0.632. In percentage, it is 63.2%. 63.2%. This may easily be seen by substituting t equals to t for the previous equation, what I said now. In the same way, if you substitute small t as 2t, then you will get 86.5%. Then 95, like that, 4t, 5t. If you see, by it is increasing, right? It is increasing. The values are increasing. Okay, the values are increasing, and there you can even find the slope. Slope for the first 63.2%. What is the slope? Also, you can find this slope. How much it will come is, if the initial slope of a curve at t is equals to 0. Initial slope to calculate. Now we are not calculating the other slopes. Initial slope at t is equals to 0. This is the, if you take this as a triangle, this slope you want. That slope, if you want, what we need to do? We need to differentiate this. If you differentiate this dc by dt at t equals to 0, you will get what? This means not this one. This equation you need to differentiate. If you differentiate this, then we will get 1 by, this differentiation of 1 is constant, so 0 minus, you will get e power minus t by t by, what you will get? T by t by d by d of e power x is e power x only. But there is other constant also present. As differentiation is given here, what you get is e power minus t by t into minus 1 by t as the answer. If you see here, this minus minus get cancelled. As t is equals to 0, e power 0 will become 1. You will get answer as 1 by t finally. Understanding 1 by t, finally you will get the answer. Okay. This slope is 1 by t. So it is mentioned 1 by t. So this graph you need to draw in the exam. They ask unit step response of the first order system. You need to draw the diagram and you need to explain. Where t is known as the time constant of the system. T is what? Time constant of the system. The output would reach the final value at t equals to t if it maintained its initial speed of response. The slope of the response curve decreases monotonically from 1 by t at t is equals to 0 to 0 at t is equals to infinity. When t becomes infinity, it becomes what? It becomes 0. Okay, 1 by t at t equals to 0. The response will decrease continuously when monotonically from 1 by, when it is 1 by t at t equals to 0. When t is equals to infinity, it becomes 0. Okay. The time constant is indicative of how fast the system tends to reach the final value. A large time constant corresponds to a sluggish system. A large time constant means sluggish system, lazy system or a slow system. A small time constant corresponds to a fast response. It is just the reverse. If large time constant, it is a slow system. If it is small time constant, it is a fast response. As you can see from figure 4.4, final value, it's percent of final value and TS2 and TS1. Okay, this is the curve effect of time constant on a system response. Okay, if the should be fast response. If the time constant is slow, then it is a very slow system. If you see from this graph, and if you see that if it is a small time constant, then it is very fast response. Okay, the error response of the system is given by, you know, whenever there is a block diagram clause like R of t and this is C of t, and if you give this feedback to here like this, here error, you know that it is input minus the from output whatever feedback C of t, right? Error is that. Even we have studied that in module 3. So R of t minus C of t, that is equal to what you will get? You will get e power minus t by t. Okay, the steady state error is given by ESS is equals to, we will limit t into infinity, limit t tends to infinity, e of t. E of t is what? E power minus t by t. So if you substitute in this infinity, you will get 0. The steady state error will be 0. That means the first order system tracks the unit step input with 0 steady state error. First order system, it will track by 0 steady state error. For t greater than or equals to 4t, okay, the response remains within 2% of the final value. The steady state is reached mathematically only after an infinite step. See, only after infinite time the steady state will become 0. The steady state is reached mathematically when it is an infinite time. Okay. Next, now we are done with unit step. Now we will go for unit ramp response of the first order system. The output response of a first order system for the unit ramp input. You know that unit ramp input has the R of S input as 1 by S square. That is the Laplace of the unit ramp. Is given by, if you in the place of 1 by, we have substituted initially for 1 by S, that is the unit step. For unit ramp, it is 1 by S square. Expanding this equation 4 in partial fractions again, you will get 1 by S square minus t by S plus t square by ts plus 1. If you calculate this again, you will get this only. You are doing partial fractions. You are dividing into fractions. 1 by S square minus t by S plus, again you are taking t common, You will get in this way. Taking inverse Laplace transform what? 1 by s square Laplace transform is t. That is a ramp. Then 1 by s is you know as it is 1. Then t is there itself. Then 1 by s plus a is what? Laplace transform e power minus at. A is what? 1 by t. So e power minus small t by capital T. So if you take t minus t common, you will get 1 minus e power minus t by t. For t greater than equals to 0 only you should take. The error signal is you know that r of t minus c of t. Okay. R of t is what? R of t minus c of t is what? T minus R of t is t only. See, R of t is t minus c of t is what? T minus t into 1 minus e power minus t by t. If you see here, these two get cancelled. You will get t minus t into 1 minus e power minus t as the. It is minus of c of t. This becomes plus. Okay. So if you do like this, you will get t into 1 minus e power minus t by t. Why? Because this is a Laplace. 1 by s square is a Laplace term. But input what you are giving as t, no, ramp function. Minus, I am explaining once again, so it will be easy for you. C of t is what you got just now. T minus e power t minus, sorry, t minus t into 1 minus e power minus t by t. If you do like this, these two get cancelled. This minus into minus become plus. So you will get t into 1 minus e power minus t by t as the answer. I hope you understood now. So and the steady state error will become when limit t tends to infinity of u of t. Whatever the error you should t tends to infinity you should do. Finally you will get as 1 by t as the steady state error. Thus, the first order system under consideration will track the unit ramp input with a steady state error at t. For the unit step is 1 by t, here it is t, which is equal to the time constant of the system. Time constant of the system. With the, it is equals to time constant of the system. The smaller the time constant, the smaller the steady state. And in following ramp input, reducing the time constant therefore not only improves its speed of response but also reduces the steady state error to ramp input. In unit step, what we have seen, the smaller the time constant, larger the steady state. And larger the time constant, smaller the steady. Like that, here it is, as t is steady state error only what t, which is equals to time constant. So if the smaller the time constant, the smaller the steady state. You need to compare in this way. This is the graph 2t for 40 and 60 and 2t, 40 and 60. This is the r of t and this is t. If you write the steady state error in this way, this is c of t signal. If you write input signal, this is the input signal. If you compare both are same. Though the steady state error to a ramp input can also be obtained by applying the final value theorem. You know final value theorem, what we have studied in the module 3, steady state error to a ramp input. So steady state error to a ramp input, final value theorem means what? T tends to infinity, you will do final value theorem means. So limit t tends to infinity of t, limit s tends to 0, s into e of s. Limit s tends to 0, s into e of s is what? R of s minus e of s. R of s is 1 by s square. Why? Because the input is the ramp and c of s is what? Whatever we got initially, that is 1 by s square into ts plus 1. If you substitute s as 0 here, if you do the calculations accordingly and take common and all, you will get answer as t. By this also it is proved that you will get the value as t. Okay. Then you have unit impulse response of first order system. Okay. For the unit impulse input, R of s is equals to 1. Unit impulse has the R of s equals to 1. And the output of the system can be obtained as C of s is equals to, in the R of s place you will put 1. You will get 1 by ts plus 1. If you take t common, you will get 1 s plus 1 by t. Taking the inverse Laplace transform, what you will get? 1 by t into 1 by s plus a is what? E power minus at. A is 1 by t, e power minus small t by capital T for t greater than or equals to 0. The response curve is as shown in figure. If you see here, the response curve looks like this. When you give it is t, 2t and 3t, how the how it is decreasing from 0 to infinity or up to 40 it is shown here. Next, an important property of linear time invariant system. In the analysis above whatever we have done, it has been shown that the unit ramp input, the output C of t is what? You get this. For the unit step, you get this. Finally, the unit impulse, you get this. These all are the equations. Comparison of the system responses of these three inputs clearly indicates the response of the derivative of an input signal can be obtained by differentiating the response of the system to can be the original signal. It can also be seen that the response to the integral of the original signal obtained by the integrating the response of the system to the original signal by determining the integration constant from the zero output initial conditions. This is the property of linear time invariant system. Linear time varying system and non-linear system do not possess this property. Only the linear time invariant systems possess this property. When if it is linear time varying as well as non-linear, do not possess the properties whatever we have seen. The time response of first order system, that property is not seen in time varying and non-linear systems. Okay, only linear time invariant system it is possible. So in this video, I have dealt with the introduction, what is time response analysis, and even did the time response of first order systems, which is and what is time response of first order systems. And in that we have seen unit impulse, unit ramp and unit step functions, how the graph of the time response is varying, either exponentially increasing or decreasing. Okay, we have seen those all things in this video. In the next video, I will do the time response of second order systems. For this topic, I am stopping the video here. Thank you from Sri Sai Tech Edu YouTube channel. Read, lead, success. Keep reading.